guys, nice to see you. So, you're welcome. So let us recall first what we discussed last time. We introduced the concept of mechanical works and considered it as a dot product of two vectors, force vector and displacement vector. So obviously work depends on the orientation between these two vectors because dot product takes into account the angle between these two vectors, so that matters. And we consider different cases when we have either simple situation when our force is constant, so it doesn't change with time, and our displacement is happening only along a single axis, so one-dimensional case for displacement. So that's probably the most easiest case. Further, we make one step in order to highlight the fact that force may be a function of position, so it will change as body moves. So this should be taken into account. So we cannot keep force constant if it changes. Another option which we also consider is when the displacement vector is not along axis x, but arbitrary position in space. So we, in particular, consider two-dimensional space. So in that case, we need to integrate, because if we consider position vector dependent force and displacement vector, which is arbitrarily oriented in two or three-dimensional space, then we need to integrate this dot product of two vectors, where one vector is a function, like force is a function of position vector, and another vector is the displacement. Obviously, we need to implement, like represent these vectors via unit vectors in order to split. You're welcome. I mean, apparently didn't like me. With this unit vectors, you can split the vector in two components or three, depends how many axes you have, and you will be able to do easier or necessary calculations, including integration of this dot product of vectors. So we consider as an example this block string system, where we calculated work done by string force, so internal force of this system, and calculated. So we show that indeed, if force coincides in direction with the displacement vector, then work is considered to be positive. If we have a different situation when these vectors are not coinciding in direction, we get negative sign for mechanical work. So this please keep in mind, because that is relevant information will definitely have an impact on your solutions when you do some problem solving. So today we continue with this related topic, and we are going to introduce kinetic and potential energy during this lecture. So if work is done on the system, this work should convert in certain types of energy. And there are actually three types of, like, which we generally consider as kinetic, potential, and internal energy. So hopefully we will have an option to discuss all of them during this lecture. Let's see how it goes. Okay, so let us start with kinetic energy. So we will consider some block. some block with mass m, and let us assume that this block is moving with some velocity, let's call it v1. So it's moving to the right, so with velocity v1. We apply some external force F to this body, and according to which law of motion it will start moving with acceleration? Second. You're right. So according to the second law of motion, obviously this body will start to move with some acceleration. At this point, we do not consider any friction, so we will come back to friction a bit later. So if it moves with acceleration, then let's say it moves some, so displacement is delta x, so it's happening along one dimension. So it reaches to some new position. So mass doesn't change, it's the same, but velocity vector will change. So we will have already v2 vector, so it will continue moving this direction. Okay, we are consistent. Ouch. And discharge. So which velocity vector will be larger in magnitude, v2 or v1? Force is exerted in the direction of initial velocity vector v1. Obviously, acceleration vector will be in the same direction. So we will increase initial velocity. Obviously, that v2 will be larger than v1. So now we can also write that according to second law of motion, acceleration will be equal to applied force divided by mass m. Now I would like you to recall our earlier lectures when we introduced and derived the kinematic equation for object which is moving with constant acceleration along a straight line. So in that case, what we had, like x, kinematic equation, what tells us? So that is already equation itself, but what it about? Hmm? Can you repeat, please? Well, yeah, sure, it is there included. However, kinematic equation tells us, like provides us information where an object will be at any moment of time. So if we are dealing with single dimension, we have x is x, means kinematic equation will give us x position of an object which moves. In our case, now it moves with constant acceleration at any moment of time. So that's the purpose of kinematic equation. And for this particular case, we can write, as you mentioned, we have x naught, initial position. We have second term is initial velocity times time, v naught times t, plus constant acceleration times t square over 2. So that's kinematic equation. We can write for velocity that it is v naught plus a times t, And as you remember, when we express t from this second equation and substituted it here in the kinematic equation, we could derive another form of kinematic equation which does not depend on time, so it represents change of velocity via change of position. So that equation looked like this. So we had v square equal to v naught square plus 2a times x minus x naught. So that was our new form of kinematic equation. Now let us work with this equation and apply it to this case which we consider when we deal with applied force F. So V2, in this case, this V2 new velocity of the block, can be represented as V2 square is equal to V1 square, which is considered as initial velocity, plus 2 times A, constant acceleration, and x minus x naught is nothing else as displacement along axis x. So we can write that this is delta x. Okay, we know how we express acceleration in this case, and we can now substitute it here. Instead of acceleration, we will write f divided by m. So let's write it down. V2 square is equal to V1 square plus 2 times f divided by m times delta x. Okay, here what we can do, let us move this V1 to the left. It will be V2 square minus V1 square equal to 2 times f divided by m times delta x. And now what we do, we multiply left and right side of this equation by m over 2. So eventually we get, let's write it here, will be V2 square, but here is m over 2, minus m V1 square over 2 equal to f times delta x. So what is this? This is mechanical work, yes, and exactly because we have displacement vector along a straight line, so it's parallel to force vector. So we remember that the work is defined as a magnitude of force vector times magnitude of displacement vector times cosine alpha, which is angle between force and displacement vectors. Here, angle is equal to 0, cosine 0 will be unity. So that's why we have f times delta x. And that will be just work. So here we can introduce new parameters, let's say k1 and k2. As you already may see that we deal already with a new concept, which is kinetic energy. So K1 minus K2, oh sorry, not K1, but K2 and K1. This is K2 and this is K1. K2 minus K1 is equal to mechanical work done on the system by some external force. So this is so-called kinetic energy work uh, theorem. So it states that if anything else happens with the system besides changing velocity, then work done by external force on the system will result in change of its kinetic energy. So we see that here the only change what happens with the system is changing velocity. Then this is a perfect example of this kinetic energy work relationship. Um, Means that if some external force performs some work on the system, um, the only result is change of velocity, means then that this work was done to change the kinetic energy of the system. And kinetic energy is represented by, so we can write here that kinetic energy is mass of the object times v square, like velocity square, divided by 2. As you see, kinetic energy increases um, quite rapidly with velocity because it's proportional to v in second power. So that's kind of a good reminder to be careful when you drive a bike, for instance. Even not such a big change in velocity in comparison to just walking, because bikes are considered quite slow and safe. However, even small change in velocity can result in quite significant increase in kinetic energy, which results sometimes, unfortunately, because of accidents to some serious damages. So this should be kind of respect. So if our force, because here we consider that this force is constant, so far we had F constant. If this force is a function of position, so what we considered previously, it doesn't remain the same, but changes from position to position, from x to x, then we, of course, need to implement integration in order to get this kinetic energy change. So we can write in that case that k2 minus k1 should be equal to integral position x1 to position x2 f as a function of x dx. So this is the way how we deal with this kinetic energy mechanical work relationship when force is a function of position, means does not remain constant. Another thing what would be good to, you have a question? So this is when force is not constant. So you see that force is a function of position, and since it changes when we move our object from x1 coordinate to x2 coordinate, we need to integrate and get the work. So it's similar what we define work for not constant force last lecture. However, it's just now related directly to change in kinetic energy. So another thing what I would like to highlight is we can take a derivative of mechanical work and introduce such parameter as power. So if we take a derivative, so it will be f times dx over dt. So first derivative over time. And that is nothing else as f times v. So in this case, that is power. And the definition of power is work done by this force per unit time. So what is velocity? It's distance traveled per unit time. So means if we have f times distance traveled, like displacement per unit time, means that work which is done by this force per unit time. So usually it's per second. And in that case, we deal not just with work because work, uh, it's the total work done to move object from point 1 to point 2. But during this travel, the power, the rate of work performance could be different. It can vary because this instantaneous velocity can be different. So the units for power usually it's denoted as capital P, and units for power as like, but this definition we can write joule per second, and that is we can represent it as also watt. So this special unit for power, which is joule, like work per unit time per second. Okay, so let us now introduce potential energy. It's another form of energy. Not always work performed by external force on a system results in change of velocity. Sometimes, as we will show it, between moment 1 and moment 2, which we consider, change in velocity will be, bless you, will be equal to 0. However, the system itself changes. Let's figure it. So that's why let us consider such system. First of all, let's define the axis. This will be some axis y, which goes vertically. And we have some zero level, which is our surface, say ground, and a block with some mass m, which resides on the ground. Then what do we have here? We have some weight mg, and let us apply some force F oriented along axis y, which is equal in magnitude but opposite in direction with respect to weight. So in that case, we can move this block somewhere up. Let's consider its new position. And this will be at the height h with respect to the ground. What is important here that initially v initial is equal to 0 and v final is also equal to 0. So we go from state 1 to state 2, which we can now call some excited state for this system, from ground state to excited state, and velocity doesn't change. So obviously this kinetic energy work relationship doesn't work because velocity doesn't change. Kinetic energy remains the same. It remains to be equal to be equal to 0. So we can even highlight here that delta k is equal to 0. So, but something definitely happened because these two states are different. Let's figure out what is going on. So work done by this external force exerted on the block can be defined as integral from 0 to h along axis y f times dy. So it's in general form. In this particular case, we write that it's equal to mg times dy, and m and g are constants, so we can take them out from the integral. So that eventually will be mg times h. So that is the work done by external force to move this block from the ground state up to its new position, which we call excited state. So that is equal to so-called potential energy as a function not of x, because we deal with y, so we put y here. So this work done by external force results, instead of changing kinetic energy, results in change of the potential energy of the system. So now we have a system with potential energy, and let us consider an option that this block from its second position, from excited position, just falls back on the surface of the ground. So in this case, we have a transformation of potential energy into kinetic energy, and we can write that potential energy at position h, which is the height of the body, will be equal to kinetic energy at position 0. So means that if we consider two extreme cases, it's excited state and ground state, when it comes back to ground state, and that corresponds to coordinate y equals 0, these values should be equal between each other. So we can write that mg times h is equal to mv squared divided by 2. From here, we can cancel out this m and get the velocity of this block at 0 level. So that will be square root of 2 times g times h. So as you see, by considering the conservation of energy when we have only initially potential energy and then kinetic energy, we can determine the final velocity of the block when it reaches back the ground level with a very simple equation. We do not need to deal with kinematic equation in order to determine how much time it will move with constant acceleration, what will be the velocity when position is equal to 0, and so on and so forth. We can apply this conservation of energy. We claim that when we don't deal with any friction, we don't have dissipation of energy, so energy should be conserved. That means if the system gains certain potential energy, it can be released in order to convert it to kinetic energy and easily calculate eventually the velocity of the block. So that is true always when we don't have any dissipation of energy. So we can write that kinetic energy plus potential energy remains constant. Let us probably consider one more example to highlight this. And that is again our old good block spring system. Let's say we have a block in equilibrium condition, x is x, then we apply some force F, which is equal to K times X, means it's equal to the spring force at any position, because once we start to compress the spring, push the block to the left, there will be some spring force F S equal to minus K times X. So with this, we will end up in some excited state. From ground state, we go to excited state. With some coordinate minus x. So let us see what will be work done by external force F to move this block from position 0 to position minus x. So work done by external force will be equal to integral from 0 to minus x, and here we substitute expression for external force. That will be k times x times dx. That is equal to kx squared divided by 2 from 0 to minus x. And we end up with kx squared divided by 2, which is our potential energy at minus x. So you see that when some external force performs the work on the system, that increases its potential energy. So this potential energy is kx squared divided by 2. And now let us see what happens when we release the system to come back to original equilibrium condition. So obviously, because of this spring force, this block will start moving from excited state at minus x along axis x to reach back its equilibrium condition. So now the question is, what will be the velocity of the block when it reaches position 0? Maximum velocity, that's true, but what the value? So imagine that you don't know about kinetic potential energy relationship, conservation of energy. What would you consider? You would say, okay, there is some initial position minus x. That's good for kinematic equation. Then what is initial velocity? Is 0, because here it's just stop. So good, we have initial position, initial velocity. However, we need acceleration also. And in this case, spring force is a function of position, means force is not constant. If force is not constant, acceleration is also not constant. So you cannot apply this simple equation which we derived previously for motion along straight line with constant acceleration, because acceleration will not be constant of this block. So means that we need to take into account in the kinematic equation acceleration as a function of position, and that can be quite challenging. So you feel that such a problem to solve is quite challenging when you want to know velocity of this block. However, with energy conservation, when we assume that friction is absent or negligibly small, we can claim that potential energy at minus x will be equal to kinetic energy at 0 position. In that case, we have k times x squared over 2 equal to mv squared divided by 2. So these 2 we can cancel out. And from here, velocity at 0 coordinate, at 0 position, will be um, given as square root of k times x squared divided by m. So instead of going to uh, time-dependent acceleration originated from time-dependent string force, we use this conservation of energy and get a very simple and straightforward equation to answer this question. What actually will be the velocity at position 0? So now let us consider friction. Introduce friction to this story because, as we mentioned earlier, friction is important. It's always, usually it matters. So the example will be based on such system. Let's have a horizontal plane. So it doesn't change in height. So it stays horizontal. Then we have some block which moves with some initial velocity v. And this block possesses some mass m, and there is some kinetic friction coefficient between the surfaces of this block and the supporting surface. So we have mu k. So what will happen with the block as it travels along this horizontal plane? Let's say plane is not limited in space, it will not fall down from the plane. Doesn't matter which velocity and mass this block possessed initially, over time it will stop because it will dissipate its energy for friction. And any suggestions where this energy will go? Because eventually this block will stop. V is equal to 0. But we had kinetic energy initially, which is m times v squared over 2. Then this guy stopped. V is equal to 0. And where kinetic energy is from? Friction. So good, yeah. So it's work done by friction force. But what is the ultimate final result of this work? Heat. Exactly. So this work dissipates, so kinetic energy dissipates in form of heat to this. So it's distributed between the plane and the body, probably in external environment. So it just start to vibrate more intensively the atoms in the lattice, crystalline lattice of the material of the plane, material of the box, also molecules of the atmosphere which surrounds this, and this energy is just dissipated. So we cannot use that energy anymore because it is dissipated. So in this case, we can write that kinetic energy was converted into internal energy. Internal energy means this heat energy. So And obviously, if we introduce internal energy into this conservation of energy system, we can write now that kinetic energy plus potential energy plus internal energy should remain constant. So this is already a general description of this picture, because it takes into account not only kinetic potential, but also the possibility for dissipation of this energy and lost it in form of heat. So now we would like to introduce a concept of so-called conservative and non-conservative forces. There are two types of forces, and let us first consider so-called conservative force. And in general, we can represent it like this. Let's say if we have some two positions, position 1, position 2, and we move object from position 1 to position 2 with a straight line. Let us change maybe color to highlight this. This is the first pass, 1. However, there is an option to move this object also with different pass. Let's say pass 2. So if for this given system work done by done to move this body from position 1 to position 2 will be independent on the pass, so work done by pass during pass 1 will be equal to the same work done by the system along pass 2, then this force can be considered as conservative. And what is also important, if we move this, so let's say we move it with pass 2 and then with pass 3, we move it back to original position. In that case, we can write that work done on a closed circle, like closed trajectory, because we go from point 1 to point 2 and back to point 1, means that's closed trajectory. So it's denoted as integral over closed path of force times dr vector, means we have definition of work here. So integral of a dot product between force and displacement vector for closed path will be equal to 0. So for conservative forces, if we move in closed circle, like it doesn't matter if it's circle or not, just closed trajectory, we come back to initial position, this force is conservative. So example of conservative forces, any suggestions what it can be? We already considered here. So most general, this will be gravitational. So that's, we can show an example here. However, as you remember, we showed a good example with string force, when work done by moving a block is like net work was calculated to be equal to 0, since this direction of the string force is changing. Then during one half of the path at negative x, work is positive. At second half of the path, when position is negative, positive already, work with negative, and net work was done equal to be 0. So obviously, if we come back with this block to original position, net work will be equal to 0 also. So that's the condition which is valid for conservative force. So let's say we have some block on inclined plane, some angle alpha, and here is this side of the inclined plane, its height h. So what will be the work done by gravitational force if we drop this block with mass m from the edge of inclined plane, or let this block to slide without friction along inclined plane? It will be mgh. mgh, you are right, and it will be independent on the path which we choose, because eventually what matters is the change of height of this block with respect to zero, the ground level. And doesn't matter, it will be zero height after falling from the cliff, or also will be zero height from sliding after sliding from the plane. So in this case, doesn't matter what is the path, the work will be by this conservative force will be the same. However, if we consider friction, that will be different, because we will have some, let's say, plane, some block on this plane. So let's say horizontal plane. And it moves to second position. So it's position 1, this is position 2. So this is new position of this block. Either we're trajectory 1 or trajectory 2. So what will be work done by friction force? It will be friction force. Actually, we have some, let's say, mu k friction coefficient. So kinetic friction coefficient. So kinetic friction force times length of this path. So in this case, let's call it S1, length of path 1. And work done by friction force in the second case, when we choose second path, it will be the same friction force, kinetic friction force. Mass is the same, reaction of the surface is the same, so it means that friction force doesn't change regardless of position of this block on the surface, times S2. And obviously, this straight line is shorter than this curved line. Nevertheless, they bring us to the same point 2 from the same point 1. So if S1 is larger than, S2 is larger than S1, S2 is larger than S1, work done in path 1 will be smaller than work done in path 2. So you see that we do not satisfy now the condition for conservative force, because for conservative force, this works should be equal, means work done by conservative force should not depend on the chosen path when we move from one point to another. So that's why friction force is a classical example of non-conservative forces. And as a result, any work done by friction force is dissipation of energy. So let us summarize our discussion today. We introduced kinetic, potential, and internal energy. We know that there is conservation of energy, means that the sum of potential, kinetic, and internal energy remains constant. So that is the key. And we have shown with some examples that it is really useful to use this concept of energy conservation in order to skip complicated calculations with kinematic equations and get, for instance, velocity at given position, even when force is a function of position, and means we don't have uh, a privilege to deal with constant acceleration. Also, we introduced two types of forces, conservative and non-conservative. So conservative doesn't depend on fast, and in the opposite, for non-conservative force, which is classical example, friction force, we have this dependence. Okay, thank you very much for attention. See you next time on Friday.